Mentioned, well, I guess it would have to be yesterday, that the topics from Unit 2 are not going away. So odds are, if you're struggling, or if you were struggling in this particular area, it might have had something to do with the act of finding the antiderivative. All right. So, for example, number 1, we look at it and we say, all right, well, the general structure ought to be limit as a approaches infinity of the integral going from 0 to, instead of infinity, a, and then all that good stuff. But the next step in the process is actually finding the antiderivative. All right. So you're longing for the days of Unit 1 where you could just type in the integral in your calculator and hit enter. The hardest part about that was coming up with the integral. Now we have the integral and we have to actually do something with it. All right. So I'm looking at the interior of the denominator, and I can see that if I were to take the derivative of that, I would get a 2x. So it's telling me u substitution, u equal to x squared plus 1, with du equal to 2x dx. Now you could ignore the limit until you actually anti-differentiate. Personally, I just worry that I'll forget about it, so I write it. All right. Unless I'm pressed for space, in which case I might skip out on that. But we're looking at an integral. Now this integral is going to be in terms of u, so unless I want to change my bounds, I'm just going to leave it boundless. All right, so I'm looking at du up top and a u squared on the bottom. So that's going to be the same as the integral of u to the negative second du. So we anti-differentiate. So increase the exponent by 1, divide by the new exponent. So negative u to the negative first. So it's going to be limit as a approaches infinity of negative u to the negative first. But so this is my u. I need to reverse substitute. So I'm going to put the u on the fly. I'll put the u back in, that u being x squared plus 1. So now that I've replaced the u with what it really is, I can incorporate the bounds, which is going from 0 to a. So I'm going to plug the a in. So negative a squared plus 1 to the negative first, minus a negative, so plus. I'll plug in the 0. When I plug in the 0, that's going to go to 1. So cut out the fluff there. It's up to you at this point. And I really mean this. I don't judge in any way. I mean, like, if you want to find the limit by hand, by all means, go for it. But the calculator is a nice way to go too. So one way or the other, you need to come up with the result. So whether you do it this way, which is to say replace, or not replace, but reorganize into negative 1 over a squared plus 1, and then apply the limit, or pop it into your calculator and use the technique I showed you yesterday. Either way, it's fine. Maybe some kind of hybrid of the two ideas. Maybe you try it, because sometimes it's easier to come up with the limit in your head than it. You'll get that done quicker than you would actually typing the function into your calculator. If that's the case, then give it a shot in your head first, and then type it in. Question.
Where did you get the plus 1 from?
The plus 1 came from substituting the lower bound in. So I plug in a 0 here. That made this a 1. Reciprocal of 1 is 1. But fundamental theorem tells us subtract that result, so subtracting a negative made it a positive. All right. Now, for this part, because when you're applying the limit, remember, limit of a constant is equal to a constant. So, you know, if you're puzzled as to how this overall became a 1, it's because this part here is zeroed out. All right. So just bear that in mind. If you're finding a limit, and it's kind of a good rule of thumb, if the bottom of the fraction outpaces the top as you go to infinity, the result of the limit is going to be 0. So this is going to stay at -1. This is going to increase without bound. All right. So this will be -1 over something really, really huge. That's going to be very close to 0. So as I get closer to infinity for A, this ratio will get closer to 0. All right. If it were the other way around, top would outpace the bottom, it would be going to some form of infinity. All right. So if you actually think of this, and this is how I made heads or tails of limits, and like I said yesterday, you spent all of, I mean, this is hyperbole, but you spent all of like 5 minutes on limits in Calc 1. It was like, here's some limit properties. Do this for homework. Now let's do limit definition of derivative. Okay, now that you know that, let's move on to derivatives because you didn't really need to know about limits. It's so important, you know. But then you get to a moment like this and you're like, yeah, you make it sound like it's really easy, but I don't know what the hell you're talking about, dude. And so if you, and this is how I reasoned it out, if you think of it as a race between the numerator and the denominator to infinity, whichever one gets there first wins. All right. So the denominator is going to get to infinity first. So that means that you're going to have -1 over something really huge goes to 0. If it were the other way around, the numerator would get to infinity first. So you would have an issue. You know, it would not be a finite value. All right. The only exception, it's not really an exception. It's more like a condition. What if there's a tie? What if they're both going to infinity? All right, now this may sound stupid. I mean, I don't know if you ever saw the movie Days of Thunder. It's like this really crappy old 80s, 90s movie. Tom Cruise and some guy. He might be Michael Rooker, you know, who plays Yondu in Guardians of the Galaxy. But then again, he might not be. Like, he's some generic 80s actor who reminds me of that individual. But anyway, it was a NASCAR movie, and like all I keep thinking about whenever I tackle a limit problem, because I grew up in that era, so I'm stuck with these kind of analogies, is that it's the race between those two guys. All right, and so if they get to the destination at the same time, they're going to end up in a crash, which is going to put them in the hospital. Or, if you were to say that in French, l'hôpital. So, if they were to both get to infinity, it would be a l'hôpital's rule situation. So, it was Cole Trickle, that was Tom Cruise, I just can't remember the other guy's name. So, part of your homework would of course, be to watch Days of Thunder. All right, it was like they were kind of piggybacking off of like the love and nostalgia people had for Top Gun by creating like the NASCAR version of it. All right, so highly recommend that. Nicole Kidman was in it. You know, that's where the sparks started to fly. You know, eventually they settled down.
How would you go about like knowing which technique to use to find the limit?
To find a limit?
Because like for example, like you said L'Hopital's rule, but if you would have done that here, you would have gotten 0, right?
If you were to do that here, you would have gotten 0 over 2a, which would have worked. Because ultimately it was going to 0 anyway. The only problem is you would have gotten lucky because we don't meet the conditions for L'Hopital's rule to apply. L'Hopital's rule, so step 1, whenever you're evaluating a limit, substitute. substitute your limiting constant in and see what happens. If you get infinity over infinity or 0 over 0, that's a L'Hopital's rule situation. If you get infinity over a constant, it's infinity. If you get a constant over infinity, it's 0. Anything else, so like maybe some sort of discontinuity, like an asymptote or something like that, that's, you might want to kick over to a calculator. You know, take a look at the picture and see what's going on. Most of the time, and this is a good rule of thumb, good strategy, most of the time it's going to work with direct substitution or L'Hopital's rule. If it does not work using one of those strategies, it's one of two possibilities. Either the limit doesn't exist, or it's complicated enough that you're probably not going to want to do it by hand anyway, in which case type it in your calculator, see what's going on. All right, direct substitution, L'Hopital's rule, calculator. Order of operations, I suppose. You know, let me come back to number 2. I mentioned this yesterday, that these are kind of placed out of order. Although I will say that numbers 2, 3, and 4 are not difficult. They don't follow the same theme of having a bound that's infinite, or at least not seemingly. All right. So let me hop down to number 5. Number Johnny 5. So again, the bounds involve infinity. Now you have a choice. This is the way I like to do it. The choice would be to follow the notes precisely and say, or the type notes, and say that the limit here is going to negative infinity, and the bounds of integration would be going from a to 2, positive a to 2. Or you could do it this way and allow for the a value to go to infinity. Why do I do it this way? And why would anybody choose to do it this way? It's very simple. Personally, I forget to write negative infinity pretty much all the time. All right, and so I'll have the right bounds. I'll have a to 2, and then I'll have this going from a to infinity anyway. So I made the adjustment in my own mind to say, you know what? If I'm always going to forget to put negative infinity, then don't try to force something that's not going to work for me. Make the adjustment here. All right, but if you know that you'll remember to put negative infinity here, then make that a positive a. All right. Either way, as long as if you were to substitute this value in here, you get what was the original problem was talking about, then you're fine. All right. So we need to integrate here. I notice that I have a constant multiplier of 2. I also notice that this is a variation on an arctangent situation. Those shortcut rules for arctan, aka the reason why I never keep your index cards after a test, because those rules, they don't stop being important. All right, especially the shortcut rule, unless you like doing trig substitution. Some of us do. On a test, I would not like to do that. You know, if I'm doing practice problems on my own, sure. You know, I'll try different strategies and, you know, get a good feel for it and see how things go. But here, I just want the shortcut rule. All right. So I know that there's going to be a 2 for this. I just need to know the shortcut for the antiderivative of 1 over x squared plus 4. All right. If it were 1 over x squared plus 1, it would be the arctan of just x. But we have an a value here, so it's x over 2. All right. So then the only question would be, is there a coefficient? Because for some of our shortcut rules, there's a little 1 over a coefficient, and for another one, there isn't. If you're in doubt, start off with u over a, take the derivative of that and see where that gets you. All right, so, you know, give it a shot, see what happens. All right, so this would be, if I assume that this is my correct antiderivative, I'd be looking at a 1/2 on top, and then on the bottom, I would, which by the way would offset with the 2, so I'm a little concerned because I ultimately want a 2 on the top. And then on the bottom, it would be x squared plus 1. All right. So clean it up. This would be 1/2 over x squared over 4 plus 1. And you say, well, that's nothing like what I'm supposed to get. I'm going to change my 1/2 to look a little different. It seems overly nitpicky. It's just I want to actually multiply it. So, all right. This should be x squared plus 4. If it's going to be x squared plus 4, then I need to multiply out a 4 here. All right, so I'm going to multiply every term top and bottom by 4. All right, so on the bottom, I get what I need. I'm going to get an x squared plus 4. On the top, I'm going to get a 2. But I already have a 2. So if this ends up being a 2 times a 2, I'm going to have a 4. That's double what I need. So that means I should have a 1/2 here. Now, if you actually know the rule, the shortcut rule for arctan as 1 over a times the arctan of u over a, then you don't have to worry about stuff like this. This is if you're figuring it out on the fly. Like, you know it's a ratio of u over a. You know it's a ratio of the square root of this to that. And you need to piece together the rest of it. It's kind of like when you're taking the antiderivative of the cosine of 6x. I think that was on the test. Maybe it was 12x. It was something like that. Maybe it was 6. I can't remember. But it's one of those things. It's like you take a little guess as to what you think the overall structure of the antiderivative is, and then check it by differentiation. All right. So now, what do I get out of all this? A lot of unnecessary work if you know the rule, but better safe than sorry. So we're looking at the limit as a approaches infinity, going from negative a to 2. 2 times 1/2. So it's this guy here. Let me break out the old highlighter here. Poor quality highlighter. Increase the highlight size. All right, that's kind of a highlighter, I guess. All right, so arctan, so the 2 and the 1/2 are going to cancel. Arctan of x over 2 on the interval of negative a to 2. Some substitution. Part of it's nice, part of it not terrible, but not the nicest thing in the world. Limit as a approaches infinity. If I plug in the 2, I'm looking at arctan of 1 minus the arctan. I'm plugging in a negative a, so negative a over 2. Now arctan of 1 is constant. So I don't need to apply limit rules for that. I just need to know unit circle. What's the arctan of 1? AKA, what angle has a tangent ratio of 1 in the unit circle? Not 60. 45. Yeah, because it was 1 over radical 3, then 1, and then radical 3. All right, we also have the same thing, but in the third quadrant. But the arctangent ratio only exists between negative pi over 2 and pi over 2. So I wouldn't care about the third quadrant anyway. All right, so pi over 4. So pi over 4 minus the limit as a approaches infinity of the arctan of negative a over 2. All right, so through direct substitution, what I'm getting from this is the arctan of negative infinity, right? Because negative, the a value is infinity, so negative infinity over 2 is negative infinity. So what I would just need to know is if I were to travel all the way to the left on an arctangent graph, where would that put me? Well, it's cool if you know it off the top of your head, but your calculator knows it, so go to your calculator. Let me just rewrite the function. This is saying the arctan of the limit as a approaches infinity of negative a over 2. So arctan of negative infinity is our direct substitution. It's going to seem like black magic. You know, well, that's not true. It would seem like black magic if I were to just spit out the answer without showing you. So let me just show you real quick. So, just typing it, almost. It's the arctan of negative a over 2, so arctan, I'll put negative x over 2. Now this would be as x is approaching infinity. So I can do a zoom trig, zoom 7, get a look at that picture, providing the calculator wants to function. Some desperate fool put their calculator in degree mode. I think there's a college algebra class or pre-calc class in here before me. So if I follow this all the way to the right, because if a is going to infinity, I'm going all the way to the right, it does look like it's leveling off somewhere. All right, so if you have no idea, that's fine. It's all right to have no idea. Go into your table set, second window, go from 0, and then give it some large value, like 100, and see where it's bringing you. Somewhere in the neighborhood of negative 1.56-ish. This whole computer is running very slow. Approximately negative 1.57. Now, if you're thinking in terms of pi, because we're talking about angles, result of an inverse trig function is always an angle. What fraction of pi are we most likely talking about when we get to negative 1.57? Well, what's pi equivalent to? What would you get if you chop that in half? 1.57, right? So a pretty good suspicion would be that this is going to negative 1.57-ish, which would be negative pi over 2. If you're unsure, you think that's the case, but you're not 100%, put in negative pi over 2, negative pi over 2 for crying out loud, and graph it. It should look like it's approaching that value as it goes to the right. Yeah, it does look like it has a little asymptote going on there. All right. Now, something to keep in mind, what's true for x for a function is true for y for the inverse of that function. All right. So there is a vertical asymptote at pi over 2 and negative pi over 2 for the tangent function, a vertical asymptote. So that would follow that there would be a horizontal asymptote. So instead of x, y, a horizontal asymptote for the inverse tangent function at those same locations. So if you know where the asymptotes are for a tangent function, then you, or the vertical asymptotes, then you know where the horizontal asymptotes are for the inverse function.
Isn't it ask about negative infinity though?
It is, but the way I structured it, I'll show you.
Because you set it as limit a going to infinity, that doesn't matter.
Well, what I did here is once I simplified it down, I would be looking for the tangent going to negative infinity. But what I did in the calculator is I just went right back to this. So I ignored all this work because I figured if you're going to do it in the calculator, get it early on and don't do all the work that follows it. All right. So if I wanted to, what I would do, if I wanted to actually evaluate this one, I would type in the inverse tangent just of x and then bring that to negative infinity. And you'll see that that's the same thing.
For each of these functions, could you just write like negative 1.57?
Just be mindful of the instructions. If it asks for an answer in a particular form, then follow the instruction. If it says round, then round. But if it says put it in terms of pi, then you would want to put it in terms of pi. So, yeah, it can be a little daunting when it comes to that. But let me just show you real. All right, so there's like digging a crater into my eardrum. It's like terrible. I think it's gone though. So there's a discontinuity when x is equal to 1. Right? So the way we handle that is by saying, let's find the limit as a approaches 1, not infinity, going from 0 to a, of dx over the square root of 1 minus x squared. All right, so basically what we're doing is we're systematically looking at this rather than intuitively and saying, well, let's just pretend that the 1 isn't there. We'll just put a dummy variable in for the 1, right? The issue is, I mean, if you were to create this graph, and we have looked at basically every kind of graph that you can look at, inverse trig graphs and radical functions and logs and exponentials and stuff like that. If you were to look at this, you'd see, you know, some reasonable characteristics, and you'd be able to kind of come up with what you would think would be a reasonable approach, except it wouldn't account for the fact that you could never actually get to 1. All right. So what we're going to do is find the limit as a approaches 1 from the left-hand side. All right. So, and that's just related to the number line. If I'm going from 0 to 1, if a is taking the place of 1, then I can't be approaching 1 from the right because there's nothing to the right. All right. There's no points to the right. And in fact, that's related to the nature of a radical function. But regardless, even if there were points to the right, I only care about the values between 0 and 1, right? But I'm coming at 1 from the direction of 0, which is the left-hand side, all right? Sometimes that plays a big role in finding your appropriate limit, and sometimes it doesn't matter at all, depending on whether it's substitutable or if you have to go to the calculator, all right? The good news is in this one case, maybe not just this one case, but in a case like this, is that this is a very basic rule. The antiderivative of dx over the square root of 1 minus x squared is what? Nobody wants to answer because I said it's a very basic rule, and if you get it wrong, you're going to feel like a fool. But just say it. No. I'll start you off. Arc. Sine. Yeah, arc sine. Yeah, it's the arc sine of x. Yeah. So it would be the arc cosine if it were the negation of this. It would be the arc secant if these two bad boys were swapped x squared minus 1 instead of 1 minus x squared, but it also had that funky absolute value of x on the outside. So really, it's the arc secant that's the most complicated looking one, and honestly, it's the rarest one. Arc tangent comes up pretty frequently. We've seen that a bunch of times already, but that's the one that doesn't have a radical in it, right? But also has a plus sign. Now, we're at the point here where I could just do direct substitution. Arc sine of A. Now, just for the sake of making it look nicer, I guess, writing less, I don't know. I'm just going to do it this way. All right, I'm only going to write the arc sine of A. I'm not going to write the arc sine of 0. Why is that? Because it's 0. Yeah, it's going to 0 out. All right, so I'm looking at the limit as A approaches 1 from the right. All right, so whether it's a left or right-hand side limit, thinking back to Calc 1, these are very intimidating because it was the first time you were experiencing some funky math notation. But it really didn't amount to much in most cases. If it's something that you could evaluate, then evaluate it. And what I mean by that is just substitute. Plug it in and see what you get. Because if the function exists at that point, then it doesn't matter if you're coming in from the left or from the right. Right? Assuming that it's a continuous function. All right? So do we know what the arc sine of 1 is? You just type it in. Pi over 2. Now, if you're trying to reason out what an inverse trig result is, one thing you want to consider is what an inverse trig function tells you. Right? It's always a function of a ratio giving an angle. All right? So if you have a good mental picture of the unit circle, then what you're doing when you're dealing with inverse trig is you're starting with the coordinates and your result is one of the angles. All right, we want the angles in radians. Sometimes the stopping off point is degrees. All right, so you might say, okay, well, 90 degrees and then take the extra second and convert that over, that's fine. But if you have a good mental picture, like if you know that at 30 degrees, the coordinates are radical 3 over 2 comma 1/2, and I say find the arc cosine of radical 3 over 2, you now know it's 30 degrees corresponding with pi over 6. All right, so that's how important the unit circle is. And hopefully you can see why I'm quizzing you on it, right? Like it's coming up, it's happening. You need to know these things. Until you get to Calc 3, in which case radians go out the window and you're back to degrees.
Is it just a coincidence that if you put that in the calculator, it gives you the same answer?
No, it's not a coincidence. It works out perfectly because the arcs. Oh, you mean this bad boy?
Yeah.
Yeah. So it's not. I wouldn't say it's a coincidence. What you're getting in the calculator is an approximation, and so sometimes that approximation could be sufficiently different from the exact answer to the point where you get something that maybe rounds to something that's slightly incorrect. And so then it's a question of like, well, did you do any calculus to get your answer? You know what I'm saying? Whereas in this case, it actually works out nicely just because this is a known function to the calculator. But the funkier you get, you know, even with definite bounds, the funkier the function, the less likely it is to play out the way you want it to. All right, so you just got to be careful. But it's a good question because the rules of the course are still in effect, and that is if it's a definite integral, it's fair game to just pop it in your calculator. So if you can get the correct final answer, you know, in the appropriate form, the way the question's asking it, then just pop it in. All right, but just be mindful of the fact that sometimes it's not going to come out so nice. You might have to adjust. So everything else is some kind of variation on these ideas. Number 3, and this I think was the last thing we'll do for this page before we move on. This is a greasy looking one. And I'll tell you, it's problems like these where, you know, you look at it and it's like, I don't know, is that integration by parts? What is it? Is that it's not a rule. So the strategies when you're dealing with integration are always going to be work from the beginning of the course to the end of the course. But we have a vertical asymptote at x equals 0. So this is an improper integral, all right? So we're looking at a case where the points don't exist at the lower bound. So I have to make an adjustment. So I say that the limit as a approaches 0, now this would be from the right-hand side, because regardless of what the natural log of 2 is in decimal form, it's something bigger than 0. So if you're going to approach 0, you'd have to be approaching it from the right. All right. So going from a to ln of 2, we have e to the 1 over x squared dx. All right, so if I'm working from the beginning of the course to the end, I'm looking at u substitution. Wrong test. I have these like moments. They're like senior moments, I guess. I could have sworn that I put this problem on the test. Oh yeah. It's not quite the same, but it was very similar to number 1 on the last test. That one was e to the x squared over 2x to the negative first. Right? But it's still, the same general idea where you have an exponential, and when you have an exponential, a good idea is to let u be equal to the power that the exponential is raised to. So I'll write that as x to the negative first, du is equal to negative x to the negative second dx, which could also be thought of as negative 1 over x squared dx, which is part of the integral, which is great news. Okay, so it's at this point that we know we're on the right path. Right? So I don't have a negative 1 over x squared in my integral. I have a positive, so let me just kill that negative. So negate both sides. And we'll be rocking and rolling here with a limit as a approaches 0 from the right, going from a to the natural log of 2. And this would be just e to the u, du. Now, I'm going to erase the bounds. I shouldn't have put them in to begin with, because it's not, these are not u bounds. If you want to make, like I said before, if you want to make the adjustment, you can, but it's making it unnecessarily complicated. Right. So the recommendation, just like I said before, is to wait until after you've integrated to bring those bounds in. So limit as a approaches 0 from the right. This would be the antiderivative of e to the u is e to the u, with u being 1 over x. So it's e to the 1 over x. Negative e to the u, very good, thank you. So negative e to the 1 over x on the interval of a to the natural log of 2. So limit as a approaches 0 from the right of negative e to the 1 over ln of 2. And it would be minus a negative, so plus e to the 1 over a. All right. Now, you get to this point, it's like all the other questions. We did the antiderivative part. You have something that you can put in your calculator now if you want. I'm not worried about this piece here, because no matter how complicated this looks, it's still a constant. There's no x in there. All right, negative e to the 1 over ln of 2. So basically, my answer here is going to rely on whatever this is. All right, so if I can figure out what this is, then I'm in good shape. If I can't, then I'm in the opposite of that, I guess. All right, so negative e to the 1 over ln of 2 plus the limit as a approaches 0 from the right of e to the 1 over a. All right, now something involving limits that, again, is often neglected, misunderstood, is that the functions, they transcend the limit, right? So if I had, like we were talking about square roots, if I had the limit of a square root, that's the same as the square root of the limit of whatever is contained within the square root, all right? Exponential functions, log functions, sine functions, arc sine functions, they're just fancier square roots, all right? They do basically the same thing. They're an operation on a particular variable. All right, so what I can do here is I could find e to the limit as a approaches 0 from the right of 1 over a. So figure out this bad boy, and you got it. And that's something you could even do analytically. All right, because there's a vertical asymptote at 0 for this function, y equals 1 over x if you want. There's a vertical asymptote. It's just a question of, is that one going to infinity or negative infinity? Well, if I'm plugging in a number that's to the right of 0 for a, what kind of result am I going to get? Positive or negative? Plug in a number to the right of 0. What kind of number is it? Positive. All right, so if I know that I'm going for, either to infinity or negative infinity, and I just told you that I'm only plugging in a positive value here, this must be going to positive infinity. So that's telling me that after all of that, the result is infinity. Because e to the infinitieth power is infinity. Subtract this minuscule value from infinity, it's still infinity. All right, but this is some funky business, which can be completely avoided if you go in the calculator and explore. Now I'll talk you through this one in a sec, because this is not going out to infinity. So doing it in the calculator it requires a slightly different approach. All right. So actually, let me type it in, and then I'll switch over to the screen. And again, if you're doing it in the calculator, you want to do it at your earliest convenience. So you don't want to wait until you've done all the algebra, because what if you screw something up? You don't want to bother with that. The minute you get the antiderivative, you pop it right in your calculator. Oh, that's right here. All right, so I put it in my calculator. Closer so you can actually hear me speak. So I typed it in the calculator. You can look at the picture, do a zoom 6. We're approaching 0 from the right. All right, so I think I got what I need out of the graph without exploring the points. Because if I'm coming in from the right, it does look like I'm going up forever. As I get closer and closer to 0 from the right, it does look like I'm increasing without bound. All right, but if you want to do it by points, the way to handle it is change your table setting. We're centered around 0. Make your change in table something very, very small, like 0.0001. I made it too small. All right, so let me make that a better option. Do like, we just do 0.01. All right, so it looks like from the left, it seems to be settling in at a constant value, but we don't care about the left. from the right, if you're following the points, it's 7.2 times 10 to the 10th power, then 3 times 10 to the 14th, then 5.2 times 10 to the 21st, 2.7 times 10 to the 43rd. It's increasing dramatically as you work from the bottom of the table to the top. All right, so you're looking at something that it's definitely approaching, visually and numerically approaching positive.